Okay, what else do we want to be able to measure? Got through a lot of them. So you had one before, didn't you, Aaron? Right on the board here, the electricity. Yeah. So what do you want to measure electricity, which particular, there's lots of different electrical things, so which particular electrical thing do you want to measure? Volts? Okay, so I need a bit of rubbing here because I've run out of room, but you've all got this down, haven't we? So if I just start rubbing from the top here somewhere. So we're going to go volts measure a thing called potential difference, which you'll also see often referred to as voltage. So the unit is indeed a volt, and the symbol is a big V. What other things can you measure to do with electricity? Amps, okay. So that's the measure of electric current measured in amps. And we also have this couple more. We have electric charge, which is measured in coulombs, which is a capital C, and electric resistance, which is measured in ohms. A couple of things here, looking at this. One is this squiggle I've just done. Does anybody recognise that squiggle at all? What is it? Yeah, it's an omega, which is one of the letters of the Greek alphabet. Okay, so quite a lot in physics and engineering. We have letters that aren't all just English, normal Arabic letters. We use Greek letters as well. We sort of run out of number of letters, which is cool, so we go into the Greek alphabet a bit, and by the time you've finished your diploma, you'll have probably seen just about every Greek letter. Maybe not an iota, I don't think that's used much, but most Greek letters you'll see. Okay, so that's a Greek letter omega. Okay. So that's the capital omega, and a small omega looks like a sort of a curly W. Yeah. So it's like a capital A and a small a look different. So a capital omega and a small omega look different. But we'll keep talking about those things as we come to them. So that's the first thing. Second thing is, anybody spotted, now that I've rubbed them all out, it's hard to see, why I'm writing some things on this side and some things on this side. I shouldn't have rubbed them out before I asked that question. But what was different about all the things I had on this side compared to the ones on this side? Laura? That is now, but before when I had things like joules and watts and all those sort of things, they're very no, they're both the SI system, yeah. No, they're all, because you've got mass and stuff, and we had newtons over here, which was kilograms, meters per second squared. So I had sort of a mixture of on both. Yeah, okay. So these ones are what are called the base units. So they're just one thing. I haven't said, they're all terms of, I've told you a story about where all these things come from. So these are all things that are defined themselves, and these ones over here you build up from those ones. So we talked about speed being, come across the we had speed being meters per second. We had force being kilograms meter per second squared. We had acceleration being meters per second per second. Yeah, we had joules being newtons, which are kilograms meters per second, times another meter to make it into joules. And then per second, so divided by another second to make it into watts. So all those things are made up out of these guys. Okay? So basic units, derived units is what they're called. Okay? So these ones here, electric charge is an amp second, a volt is a joule per coulomb, and a ohm is a volt per amp. Yeah, so they're all built up from these other ones. Yeah, brilliant. Going really well, really, really well. Yeah, I can see it. Anything else you want to be able to measure? There's 7 base units, so you've got 5 of them, which is pretty good. It's about what most classes get. Often there's temperature takes quite a lot, so you've done well. You've got the 5 basic ones that you'll need. There's 2 pressure. Okay, so pressure's over this side. So pressure, any idea what the unit for pressure is? Yeah, actually just the PA, so just the Pascal, which is PA. Yep. So if you've got 1,000 pascals, it's a kPa, a kilopascal. So you can certainly you will be working much more with kPa than you will with Pascal, right? Kilopascal. And if it's on this side, I should be able to work it out in terms of these turkeys. And a Pascal is 1 Newton per square metre. Okay, so we've done the 1 Newton thing, so pick up your 1 Newton force again, feel the force, yep. Your 1 Newton force, and imagine it's spread over 1 square metre, so the desk in front of you. So if you take this force and spread it out evenly across your desk, then the pressure that's pushing down is about 1 Pascal, okay? Which again is not very much. So we tend to do all our engineering measurements, you'll definitely be in kilopascals. Even megapascals, and there's some things you'll measure in gigapascals, which is 1 billion pascals, so a lot of pascals. Yeah. Cool, so pressure's not the extra thing over here, but it's a really important engineering idea, one you'll definitely be using a lot. Any other random guesses? So vacuum, there's a lack of anything, so there's better be pressure, air pressure or something. You can say when the pressure's 0, it goes to that. What? Displacement is the proper word for distance that we had right at the start. Torque, okay, again, we're going to do that. So torque or moment of force is the language for torque. And it doesn't actually have a fancy name for the unit. It's measured in Newton metre, which is just Newton times metre. That makes sense. That box was quite heavy. I'm not going to do my next bit with that sitting on the table. Okay, so we'll look at this table again. If I want to make this table turn, so I'm going to make it turn, the table's going to turn that way. So this end's going to come up, that end's going to, the whole table's going to lift up. Okay, here we go. 1 finger. 1 little finger. Yep, I can make the table turn with 1 little finger. Now I'm going to try and make the table turn again by pushing it here. I actually have to hold it down this end to make it turn when I can just about do it. Yep, it's really hard work. Okay? No way I can do it with 1 little finger. So if I got a small force and a big distance, I get a certain amount of turning. And to get the same amount of turning with a small distance, I need a big force. So I'm multiplying the force and the distance. Force and the distance. Yep. So small force, big distance will give me exactly the same amount of turning as small force, big distance. Yep. So that makes sense that it's really, units are really cool. You can look at them and go, oh, yeah, talk's got these two things going on. Once you understand it, it's really, really useful. So again, it's not the answer to this side of Aaron, but it's another really important thing you'll definitely deal with. You've got most of the engineering ones. You've done really well. There's one over here that I don't think you'll use in your engineering diplomas, but it's something that you'll think about. Oh, this makes sense to measure. Just look around the room and you should go, I wonder how I would measure that. Brightness, light. Yes, yeah, so someone pointed at the light and someone said brightness at exactly the same time. So the proper unit is luminous intensity is the unit, and is the quantity, and the unit is a candela, which is CD, a candela. Comes from the old idea of a candle. So basically 1 candle power is where it comes from, is the unit. So how much light 1 candle puts out. It's been defined, I'm not sure what the details are, but it's been defined differently, probably in terms of atoms or something. Again, it's got a more precise definition than candle now, because that'll depend on what type of tallow it's made of and all sorts of things. But that's where the idea comes from. So the candela is 1 candle power. Just trying to think if there's any other really important ones on this side before I give you the last one over here. Unless anyone has done chemistry. If you've done chemistry and you've measured concentrations in chemistry, you may remember the viscosity would be on this side, which is a measure of how thick a liquid is, so how easily it flows, and you basically measure it in terms of the amount of force it requires to move it, and speed and stuff. So it comes back to the things we've already had. So if you did chemistry, you might have measured something per litre as a concentration. pH levels. Okay, so pH level really goes with the angle one. So pH. It's a long time since I've done chemistry. Negative log to the base 10 of the concentration of the hydrogen ions, I think. So basically you work out the concentration, that's what the square brackets mean, of hydrogen ions, and then you take the log of it. So it's a measure of concentration of hydrogen ions in the stuff. So the question is, you're getting close, what do you measure the concentration in? I don't know, has anybody ever heard of moles per litre? Moles per litre. Okay, so we measure it in moles. So the last one over this side, which I'm going to have to make some space for, it's technically called amount of substance. And these ones are the basic units. So over this side we have all the basic units. And on this side we have the derived units. Yeah. So you done really well. So the question of what is a mole? So I've sort of explained what the other one, and you've got a feel for the other ones. You know what a metre is, you know what a second is, you know what a kilogram is, you know what 1 candle looks like. You've got good ideas for all of those. So let me explain to you what a mole is. So I'm going to say a few words, just a few sentences. I just want you to imagine what I'm saying. Okay, so here we go. So a dozen eggs. Imagine that. A dozen chairs. A dozen bread rolls. I might see those in a few minutes. A dozen elephants. You got it? Yeah, no problem. Okay, I'm now going to just say the same thing and just slightly different, and I want you to imagine it. A mole of eggs. A mole of chairs. A mole of bread rolls. A mole of elephants. What's the problem? What's the question you really want to ask? How many? Yeah? So when I say a dozen, you've got 12. Have you got an idea in your mind? When I say a mole, you're going, what number am I meant to have? Yeah? Okay, so the answer is this number. just clear a little bit of space to write the number on the board. Beating us a bit more. Here we go. This is the number. When I said a mole of eggs, this is the number you should have imagined. That many. That's how many things there are in a mole. And this is why it's used in chemistry, because a mole of carbon atoms is about 12 grams. Okay? So it's sort of like a nice size of the stuff, the sort of stuff you can measure. So we do moles per litre. If you took that many carbon atoms and dump them into water, you have a concentration of 1 mole per litre. And that's the same as putting like a tablespoon into a litre. So that sort of works out about the right size for chemistry. Okay. You all remember that number? Roland has. I saw him doing it. Okay, Roland, what was the number?
You just said 6 and a whole of eggs.
What was the number I had on the board? I saw you going.
I started counting, I gave up.
Ah. Did anyone do it? Who said that? No, someone said, this is James, what? Well done, that man. Okay. You're not going to say that number by going 6 bazillion, trillion, quadrillion, duckillion, or whatever comes next. I don't know. You're going to count the number of zeros. So it was 6 with 23 zeros, wasn't it? Okay. Because we're going to be engineers, we've got a way of writing that. All you do is you write 6. That's what that means. That means 6 with 23 zeros. Yeah? Really important number. Really important that we can write these numbers, big numbers, without having to write lots of zeros. Because sooner or later, you'll forget. You'll miss a zero out. You'll stuff something up. It's meant to have 9 zeros, you'll only give it 8. And then it'll carry on to the calculation. Your building maybe is 10th of the strength it should be. Dropping a zero is pretty serious. You suddenly get 10 times as much concrete as you need, or 1/10 of what you need. So that's a shambles. Yeah. So we need a better way than having to write 23 zeros every time. You've got to have a system. Okay? So this is what we call scientific notation, and this is what we're going to work on next time. We're going to look at that, and that'll lead us into all the millis and kilos.